Okay, so let's start with the first lecture. I'd like to go with the elementary set theory. Let me do the PowerPoint. For example, we said that the set is a collection of objects. We're trying to define all of the objects that belongs to the set of E. For example, the 5 characters in the animation Doraemon, and they all belongs to the set of E. Elements within the set is called the objects. So for example, Daihong, that belongs to the set of E. We usually use the Venn diagram to indicate what are the relationship between the different sets. For example, we draw a circle to indicate that is the set of A, and this is the set of B. If we see any overlapping between the set of A and B, we say those are the elements that belong to set A, as well as they belong to set B. If we say that B is a subset of A, that means all the elements within the set of B would also belong to the set of A. But beware, not all the objects within the set of A could belong to the set of B. The set operations, the first one is called the union. So we have the notation A union B, that's indicating any objects that belong to A or B is equivalent to say X belong to A or X belong to B. So the gray area indicates the union between A or B. Intersections, that means this is the upside down U. Okay, we can say this is the intersections of set A and set B. So that indicates only the area overlapping the set of A and set of B. So if we say an object X that belongs to A and B, that means X only belongs to this gray area. Thirdly is the complement. In some of the textbook, we have the upper score to indicate the complement, or a little C on the top right-hand corner to indicate the complement. Complement, that means not set A. Okay, so if we have, this is a set of A, not A, so that's indicate anything outside of A. We can make use of the theories to look at the different laws. For example, this is the first distribution law. The first distribution law says anything that is in A or brackets B and C is equivalent to say that this subject or this object belongs to A or B and A or C, the right-hand side. Okay. If we want to look at it in the Venn diagrams, I'm trying to point it out to you. Hopefully you can get it from this Venn diagram. So from the left-hand side, let's first look at the brackets. What is the area of B and C? So this is B, and this is A. This is B, and this is C. B and C would be that little common area between B and C. And then outside of the bracket, A or B and C. So that is the entire A and this little intersection of B and C. So on the left-hand side is indicated by the shaded area. On the right-hand side, let's look at it. A or B, that would be the area within the circle of A or the circle of B. A or C, that would be the circle of A and the circle of C. But we have N in the middle. Okay, so this is more straight. So A or B and A or C. So we are only looking at the intersect area, the overlapped area for the N. So in this case, again, the right-hand side is indicated by the shade area. So we prove our first distribution law just by looking at the Venn diagram. But I like to do that mathematically. So if I have a proof to show you this way, the distribution law, just the same as we indicated in the PowerPoint. So here is the proof. If I have an object, let's say X, belongs to the left-hand side, A or B and C, and I expand it, X belongs to A, or, because of this or, right? Or X belongs to B and C. The next step, I like to put it into I want to widen that relationship. X belongs to A, or X belongs to B, and X belongs to C. So I'm trying to expand this bracket. Now the next step is I'm trying to look at that or relationship. So if this two belongs to one group, I can expand this into X belongs to A, or X belongs to B, and X belongs to A, or X belongs to C. Okay, so I'm trying to expand this relationship. Now, on the first objects in here, so we're equivalent to say that X belongs to A, or X belongs to B, and putting that X belongs to A, or X belongs to C, and put it back into the same notation. So we are having X belongs to A or B, and X belongs to A or C. And that's proved the distribution law. If we look at some of the practical examples, for example, we have a set of A, have 4 numbers, 1, 2, 3, 4, B, 2, 3, 4, C, 4, 5, 6. Let's look at the left-hand side. B and C, if we have the common or the overlapping of B and C, it would only be a 4. But if we have A or B and C, so we have the whole set of A, 1, 2, 3, 4, or B and C, 4. So the left-hand side would consist of the 4 elements of 1, 2, 3, and 4. What about on the right-hand side? A or B, so that is all the elements in A or B, so that would be 1, 2, 3, 4. What about A or C? So we would have 1, 2, 3, 4, 5, 6 all together. But we have N in between, so we look at the common elements between A or B and A or C. So that is only consists of 1, 2, 3, 4. So in this case, we just proved the left-hand side equals to the right-hand side of the distribution law. Okay. The second distribution law is this one. A and B or C is equivalent to say, is equivalent to A and B, or A and C. The next one is called the De Morgan's law. So first of all, we see that the complement of A or B is exactly to say that's the complement of A and the complement of B. So what happened in the Venn diagrams, we can see that, for example, we see the A or B is the yellow area. The complement of it would be all the shaded area outside of A or B. And that is exactly what we are trying to say is equals to not A and not B. The second De Morgan's law is the A and B complement is equivalent to not A or not B. So that would be within this area. Okay, So you can find some of these set theory as a very basic elementary theory for you to understand how we represent some of the sets or some of the objects within the sets.